Thank you to all of you for coming out tonight, despite the clouds. So tonight I'm going to tell you about gamma-ray burst. And as I've said here, these are the biggest explosions since the Big Bang itself. I love gamma-ray bursts. Okay, I've been studying them for about a decade now. And I find them fascinating for several reasons. First, as David mentioned, they're the biggest explosions since the Big Bang. I'm a guy, I like explosions. So that's the first reason. Second, they represent a lot of the extreme objects in astrophysics. The most massive stars in the universe, neutron stars, the birth of black holes is marked by these gamma-ray burst explosions, as we'll discover tonight. They also push astronomy itself to the limits. So in a lot of astronomy, we look at objects that have been there for billions of years and will continue to be there for billions of years more. Gamma-ray bursts last for only a few seconds, up to a few hours. And so when we study them as astronomers, we have to be very quick, right? Otherwise we miss it and we have to wait for the next one. So this is kind of like astronomy in the emergency room. We do everything quickly. It's astronomy on steroids for those of you who have been following the Lance Armstrong saga. And finally, I find them fascinating because I think that they represent serendipity in science. Nobody has ever predicted gamma-ray bursts. They were discovered completely by accident. And that set off a chase that has been going on for about 40 years now, involving hundreds of people around the world. And so tonight I want to take you along on this chase, tell you a little bit about the history and where we're going with the study of gamma-ray bursts. Now, if none of this convinces you that gamma-ray bursts are interesting, you should just look at some of the pictures like this. Gamma rays of doom, why you should worry about merging neutron stars. Or a gamma-ray burst frying the Earth. So gamma-ray bursts are going to kill all of us, so pay attention. Okay, so let's start at the beginning. What are gamma rays? Okay, so this is the electromagnetic spectrum, simplified. And this is the visible part of the spectrum that we see with our eyes. At longer wavelengths, we have radio waves, infrared. As we go to shorter and shorter wavelengths, we see the ultraviolet part of the spectrum, the X-rays, and then the most extreme form of light, gamma rays. Okay, so gamma rays are the most energetic form of light. They have the shortest wavelengths, about the size of an atomic nucleus, very short wavelength. And what's important for our story of studying gamma-ray bursts is that gamma rays cannot penetrate the Earth's atmosphere. So that means that as we sit here tonight, the atmosphere is shielding us from gamma rays coming from outer space. It also means that the atmosphere is blocking our ability to see gamma rays from outer space. Okay. So the story of gamma-ray bursts actually ties to the beginnings of us launching satellites into space. And like a lot of fascinating stories, it starts in the middle of the Cold War, at the height of the Cold War. The US and the Soviet Unions have been undertaking these nuclear explosions for many years. And in the early 1960s, they decided to sign the Limited Nuclear Test Ban Treaty. And the important part of the treaty for us reads that it is meant to prohibit, prevent, and not to carry out any nuclear weapon tests in the atmosphere beyond its limit, including outer space. Okay. So here's a picture of President Kennedy in the Oval Office signing the treaty. Now, there was very little trust between the two sides, of course. And so as soon as the treaty was signed, the US decided that it had to find a way of monitoring compliance of the Soviet Union with the treaty. And what they decided to do was to launch satellites into space that could detect the signature of a nuclear explosion. And so here are some pictures of these satellites, an artist's conception of these Vela satellites. Vela coming from the Spanish word velar, which means to watch or to guard. You can see the scale of the satellite. They're about the size of a person. Here's Kennedy inspecting one of these satellites. And so the US launched these satellites into space, and they launched them in pairs. And the reason to launch them in pairs was so that they could triangulate the direction from which the gamma rays came and pinpoint any nuclear explosions, checking whether the Soviets were violating the treaty. And a few years after the launch, the satellites found this. Okay, so what are we looking at here? This is the number of gamma rays detected per second by the satellites as a function of time. And so you can see that for a brief period of time, for about 6 seconds, these satellites detected this enormous burst of gamma rays, the exact signature of a nuclear test in space. Okay, so of course that got everybody really excited. And this was the first event on July 2nd, 1967. And subsequent to this discovery, they found more and more of these events. And eventually they realized that these events were unlikely to be nuclear tests. There were too many of them. They were not coming from the right direction. And eventually they decided to declassify this information and notify the community that there are these sources of gamma rays, bursts of gamma rays coming from outer space. And so the news was announced in a paper in the Astrophysical Journal in 1973 by 3 scientists at the Los Alamos National Laboratory, which was in charge of running the satellite mission. And the title was Observations of Gamma Ray Bursts of Cosmic Origin. And the important part that they said in the short summary of the paper is that directional information eliminates the Earth and the Sun as sources of these bursts of gamma rays. So they were not coming from the inner parts of our solar system. They were coming from somewhere else, somewhere further away. Okay, so this was an enormous discovery. This is what really set off a large number of people to try to understand what is going on with these sources. So here's a little gallery of what gamma ray bursts look like. So in each panel, on this direction is the number of gamma rays detected by the satellite, and this is the duration of time during which the burst was detected. And you can see that they look very different from each other. Some of them have many spikes. Some of them are just a single spike. Some of them, like this one, last for less than a second. Some, like this one, last for about 300 seconds. Okay? And so, this, as the saying goes, if you've seen one gamma ray burst, you've seen one gamma ray burst. Okay? There are really no two that are alike, which is really amazing, even though we've been looking at these types of sources and collecting them for about 40 years. Now, to give you a sense of scale, let's think about this. The US decides to launch these fairly primitive satellites into space, the first time we've ever put gamma ray satellites in space, and immediately we discover these sources. That means they must be quite bright. Okay, but how bright are they? So here's a map of the sky in gamma rays. If our eyes were sensitive to gamma rays and the atmosphere did not block them, this is what we would see. So here down the middle of the map is our Milky Way galaxy. And then you can see that as we go away from the Milky Way galaxy, the gamma ray sky becomes dark, and there are a few sources here and there sprinkled around. Now what happens when one of these gamma ray bursts occurs? So here's the same map. Here's a gamma ray burst occurring. Boom. Okay? Do you see that? For a few seconds, just a few seconds, briefly, it outshines the entire universe in gamma rays. Okay? Just to set the scale. It becomes brighter than anything else in the sky. The Milky Way galaxy, any source that we know of, just for these brief few seconds. And that's the reason that even with very simple satellites, these objects immediately popped up and were discovered. Now, in fact, they do have an impact on Earth, too. Some of these gamma ray bursts are so bright that the number of gamma rays hitting our atmosphere actually produce what's called an ionospheric disturbance. So here's a measurement of the ionosphere, of the Earth's ionosphere. And you can see that here there was a gamma ray burst. Here is the gamma ray burst. And you can see that the response of the ionosphere to the gamma ray burst, essentially the ionosphere shrinks in a little bit because it gets bombarded by these gamma rays coming from outer space. So think about the amount of energy that's required for something so far away to actually affect the structure of our atmosphere. And that's part of the reason why, if one of these objects were very close in, it could fry all of us. Okay, so these objects were discovered. They were announced in 1973. And for the first 20 years, nobody had any idea what was going on. In fact, by 1993, this compilation came out. I don't want you to try to read this, of 135 different theories for what could be causing gamma ray bursts. And at the time, there were only about 100 gamma ray bursts known. So there was more than one theory per burst. Okay, this is great. Now, to most of us, this would seem like a terrible situation to be in, right? So many theories, so few gamma ray bursts. To theoretical astrophysicists, this is fantastic. right? It's like being, kids left alone in a candy store. You get to do whatever you want. And so they came up with a large number of theories that were motivated by two facts. One is that these objects have a very short duration. They only last for a few seconds, maybe a few hundred seconds. And the other one is that they're very extreme in their properties. They produce gamma rays. They don't produce visible light or radio waves. They produce gamma rays. So they came up with ideas for maybe this is a new type of exploding stars. Or maybe these are giant flares from other stars that we've never seen on the sun. There was one theory that said that maybe these are comets composed of antimatter colliding into stars composed of normal matter, producing these gamma ray bursts. Maybe black holes colliding with various stars or other objects in our galaxy. And even interstellar warfare. I mean, after all, they set to find nuclear explosions in space. Maybe they just found bigger explosions coming from other planets. So what was the problem? Why were there so many theories possible for what gamma ray bursts are? And the problem was the uncertainty in the distance. All we knew is that they were not coming from the inner part of the solar system. But there was essentially no way of finding out whether they were coming from the outer part of the solar system, relatively nearby, from our own galaxy, or maybe even from the edge of the universe. And of course, the further away a gamma ray burst is, the more energy would be required to produce one of these bright explosions, and that would require more and more extreme models. Okay. So why couldn't we measure the distance? What's the problem? Well, here's a way of illustrating the problem. Gamma ray satellites are fantastic at finding gamma ray bursts, but they're not very good at telling us exactly where they came from on the sky. Okay? Unlike a regular telescope in visible light that can pinpoint objects very accurately, all a gamma ray telescope can tell us is that the gamma ray burst came from somewhere in here. Okay? And for comparison, this is the size of the moon. Okay? So this is a big patch of sky. Now, if we don't know exactly where the gamma ray burst came from, all we know is that it's in this patch of sky. How do we know whether it came from this star? Or maybe it was caused by that galaxy, or that faint star over there, or that faint galaxy, or maybe this collection of galaxies over here. Right? So without having a very precise position that could tell us that it came specifically from one of these objects, we would have no idea how far away the object is. Okay? So that was the challenge with gamma ray bursts. There were 100 of them known, but none of them were accurately pinpointed to tell us where they came from. But there was one interesting test, one interesting hypothesis that we can test even with very poor positions on the sky. And that is that if gamma ray bursts came from the Milky Way galaxy, then like the stars in the Milky Way, they should line up with the disk of the galaxy. Right? Our galaxy is not spherical, it's not like a ball, it looks like a pancake. Okay? So the gamma ray burst should come from the pancake. So that means that if we looked at gamma ray bursts in the sky and plotted their positions, they should look something like this. They should be concentrated along the disk of the Milky Way galaxy. So at the very least, even if we can't say specifically which objects caused them, if we could just measure the locations of a large number of gamma ray bursts in the sky, we can see if they come from the Milky Way galaxy or from outside of the Milky Way. That will be the first test. And so in 1991, NASA launched the Compton Gamma Ray Observatory. This was the second of NASA's great observatories to be launched. The first one was the Hubble Space Telescope. And one of the main missions of the Compton Gamma Ray Observatory was to find hundreds and thousands of gamma ray bursts and provide a map on the sky of where they came from. And so it had these detectors here on the corners of the satellite that were designed to detect gamma ray bursts. And it did so for about 10 years until it was deorbited. So what I'm going to show you is a map of what they found. So how many people think that map will show the gamma ray bursts lined up with the disk of the Milky Way? No one. Wow, you're smart. Okay. So here's the map of gamma ray bursts in the sky. Okay. So this is where we would expect them to line up if they came from the Milky Way, just here along the middle. And as you can see, they're uniformly distributed everywhere in the sky. Okay? They do not have a preferred location from which they come, suggesting that they're probably not coming from our own Milky Way galaxy. So this didn't convince everybody. And in 1995, the American Astronomical Society decided to organize a great debate to commemorate the 1920 great debate between Shapley and Curtis, Shapley over here, Curtis over here, who debated the scale of the universe. At the time, in 1920, the mystery was whether the nebulae that Hubble discovered were part of our Milky Way galaxy, or what were called back then island universes, their own independent galaxies. And so Shapley argued that they were part of the Milky Way galaxy, and Curtis argued that they were island universes. Curtis was wrong. Shapley became the director of the Harvard Observatory. Okay, so we know that galaxies are not part of the Milky Way. They're their own island universes. And the argument this time, in 1995, was similar, the distance to gamma ray bursts. How far away are gamma ray bursts? And so there were two gentlemen arguing this question. Don Lamb from University of Chicago argued that gamma ray bursts were galactic in origin, that they come from the Milky Way galaxy. And astronomer Bohdan Paczynski from Princeton University argued that no, they are cosmological. They come from the vast cosmos outside of our galaxy. Okay, so here's a picture of Don Lamb and Bohdan Paczynski right before the debate started with the moderator, Sir Martin Rees, who's the royal astronomer, still is. He advises the Queen of England about a variety of astronomy-related things. And he moderated the debate. Now, I just showed you a map that convinced, I think, all of you that gamma ray bursts are not coming from the Milky Way. So how could these two people argue about this so vehemently? Well, the reason was that around that same time, there was an interesting discovery of neutron stars. These are objects that are about the mass of the sun, maybe twice the mass of the sun, and about the size of the city of Boston. Okay, very peculiar objects. They're left behind from supernova explosions of very massive stars. Extremely dense objects. So around that time it was discovered that some of these neutron stars are traveling at hundreds of kilometers per second, zooming out of the Milky Way galaxy at very fast velocities, and populating the halo of the galaxy. Okay? Now you can imagine that if hundreds or thousands of these objects are streaming out of the Milky Way, and they had something to do with gamma ray bursts, they might produce a distribution on the sky that looks to be spherical, even though they are part of the Milky Way galaxy. Okay? And that was the argument that Don Lamb made. He said, that's fine, the Milky Way is over here, but the gamma ray bursts are coming from these high-velocity neutron stars, which are everywhere around us on the sky, even though they're part of the Milky Way. And at the end of the debate, there was a vote, and the vote was 50-50. Okay? No consensus was reached. This was in 1995. So NASA spent a lot of money to make this beautiful map, and still the astronomers were not convinced. Now, one thing that was clear to Paczynski, which he proposed in the debate, is that if he was correct, and gamma ray bursts indeed come from these very vast cosmological distances out in the universe, that means that the amount of energy released in these bursts is enormous, more than anything else we know, any other type of explosion. And so that means that maybe the gamma ray burst itself shines very brilliantly in gamma rays for a few seconds, but there should be something left behind. Just like when we burn a fire, initially we have these beautiful flames, and then we have these smoldering embers that can shine at lower temperatures, redder light for much longer. He predicted that something similar would happen with gamma ray bursts. That following the very bright burst of gamma rays that only lasts a few seconds, there would still be emission coming from these objects that he called the afterglow. And the afterglow would last, instead of a few seconds, maybe a few hours. Maybe, if we're lucky, a few days. Okay? But the other thing that's important about the afterglow is that it would not shine in gamma rays. It would shine in visible light and in radio waves, which means that if we could capture this afterglow, we could pinpoint the positions of gamma ray bursts very accurately and finally be able to tell definitively what kind of objects they're associated with. Okay, so that was the proposal. And this is essentially what we do and what we have been doing for the past 15 years or so to actually pinpoint gamma ray bursts and try to understand this mystery. So let me show you how we do it, actually. So I've been running this program here at Harvard called the Harvard GRB Program to study gamma ray bursts. So we have these satellites in space that detect gamma rays. And as soon as they detect gamma ray bursts, these satellites are much more modern than the ones from the Cold War. They let us know about it right away. So we get an alert on our iPhone. So here's my iPhone. I never go anywhere without it. This is not an advertisement for Apple. You can also get it on your Android phone. But we get the alert within about 60 seconds of when the gamma ray burst was detected by the satellite. And what we do, okay, my research group, is we immediately call up all these observatories around the world and in space. We ask them to stop everything they're doing, point the telescope in the direction of the gamma ray burst, and try to catch this afterglow before it vanishes. Okay? And this happens about twice a week. Okay? And of course, we have to respond very quickly. And some of my students and postdoctoral fellows are in the room. They can tell you that even though it happens twice a week, it always seems to be on Friday night or Saturday. Okay? But this is the fun part that I was alluding to. This is why gamma ray bursts are very different from other objects. We can't wait until next week to look at them, or the next time we happen to travel to the observatory. We have to do it right now. Of course, that makes us very popular with the people at the observatory who are trying to do their own science. So here's a little movie that NASA put together, kind of illustrating the process. So here's a gamma ray burst somewhere out in space, maybe in our galaxy, maybe somewhere else. Here's the satellite detecting it, transmits the information to the ground. You can see the telescope is already moving to that direction in the sky. And then we start taking pictures. And we look for something like this, something that's bright and fades away. Now, of course, they don't come with a circle around them. Okay. So there's a lot of work involved in actually taking these images of the sky and scanning all of the sources and all of the objects and looking for the ones that fade away that can give us the very accurate position of the gamma ray burst. So this process succeeded finally after the launch of a satellite, a Dutch-Italian satellite called BeppoSat in 1996. And this satellite was the first one of these gamma ray burst satellites that were designed to provide positions from gamma rays to observers on the ground as rapidly as possible. In that case, it was several hours, not a minute, several hours. And they had their first success in March of 1997, February, March. So these are X-ray images taken by the satellite after they discovered a gamma ray burst. Here's an image of the part of the sky where the gamma ray burst occurred from February 29th, 1997. There's this very bright source over here. Here's another image of the exact same part of the sky taken 3 days later. And you can see that the source became much fainter. Okay? So this is the afterglow of the gamma ray burst, fading away right before our eyes. But this is an X-ray light. Here are afterglows in visible light. I'm just showing you a few examples. So here's an image of some part of the sky that had a gamma ray burst taken with a visible light telescope. And here's an image of the same part of the sky taken a day later or a night later. And you can see that all these objects are the same, right? You have these two stars over here, these two over here, and these two faint objects or these two faint objects. Only right here, there's an object that was here and is gone the next day. Okay? Here's another example. These are images that we took with the Hubble Space Telescope. So here is a gamma ray burst afterglow, and here is several days later. It's gone. Okay. So these afterglows really exist. And as you can see, they provide very accurate positions. They can tell us exactly where the gamma ray burst came from. Not just some random big part of the sky, but a very precise position. Now, we're excited in particular about the visible light, because the visible light from the gamma ray burst, from this afterglow, doesn't tell us just the position. It can provide another very important piece of information, which is the distance. Okay, so how do we do that? Well, how many of you have heard of the concept of redshift? Almost everyone. Great. Okay, so redshifting or blue shifting of light is very similar to when we stand next to train tracks and we hear a train coming towards us. The pitch gets high, it moves away from us, the pitch gets low. So an object that moves away from us in the universe has its light redshifted, it becomes redder. An object that's moving towards us has its light blue shifted. It becomes bluer. Now, why am I telling you this? The fact is that the universe is expanding, right? Just like a balloon. And so objects that are far away from us are expanding away from us at a faster velocity and therefore have a bigger redshift than objects that are close to us. And so if we can measure the redshift, the amount of redshifting of light from objects in the sky, we can tell how far away they are. And the way we measure the redshift is by looking at a spectrum of the visible light. So that's the reason we want to study the visible afterglow in particular. So here's an example of the spectrum of the visible light from a gamma ray burst afterglow that we observed several years ago. It looks like a complete mess, right? You say, well, what are all of these lines and these things? Well, this is actually the specific fingerprints of different kinds of atoms in the environment of the gamma ray burst. And so some of these lines corresponds to silicon or iron or hydrogen or carbon or aluminum. And if we can identify exactly what line corresponds to what element, we can then measure how much it's redshifted compared to its expected wavelength. And that tells us the distance to the gamma ray burst. Okay? So this gamma ray burst is very far away, 12.1 billion light years away. Okay? So this object is not in the Milky Way. Okay? It is, in fact, so far away that it exploded only about 1 billion years after the Big Bang. Okay? And so that was the first solution to, or first part of the solution to the mystery of gamma ray bursts. By finding their afterglows in a painstaking process of pointing telescopes rapidly all over the sky, and then finding a source that fades away and measuring its spectrum before it's gone, we can finally answer the question of how far gamma ray bursts are, and they are extremely far away. Now, because they're so far away, that also means that they're extremely energetic. Okay? Otherwise, we would not be able to see them from these distances. How much energy is produced by a gamma ray burst? Well, it's the equivalent of taking the sun, right? Everybody knows E equals mc squared, right? If we take the sun and convert all of it into pure energy in a single second, that's a gamma ray burst. Okay? So this is an enormous scale of energy. It is, in fact, why gamma ray bursts momentarily outshine the entire universe in gamma rays, because this is just an enormous resource of energy. And in the visible light, why they outshine entire galaxies, just for this brief period of a few hours. Now, we really know of only one process that could produce that much energy in such a brief period of time, and that is to produce a new black hole. And to have that black hole accrete material, suck material into it, and produce these jets of radiation that appear to us as a burst of gamma rays. And this is what we think is happening at the heart of every gamma ray burst. Essentially, every gamma ray burst is a signal in the universe that a new black hole was born. Okay? And we find 2 of these every week. Okay? Okay, so far I've talked about gamma ray bursts as if there's just one type of object. It turns out that there are actually 2 kinds of gamma ray bursts. So here are 2 examples. Here's a gamma ray burst that lasts about 30 seconds. And here's one that lasts only a fraction of a second. Now, if we take all of our gamma ray bursts, and they all look very different from each other, but we ask a very simple question, just how long do they last? Okay? We don't know exactly, we don't care what they look like, just how long they last. Then we can make a distribution of how long these gamma ray bursts last, and the shortest ones only last for about 10 milliseconds. Okay? Just a brief period of time, an entire sun was converted to energy, a black hole was born. Some of them last a few hundred seconds. Okay? So some of them are much longer. But if you look at this, you can see that there are actually 2 groupings of gamma ray bursts. There are ones that are longer, that last maybe about a minute on average, and ones that are shorter, that last about half a second on average. And astronomers, one thing you need to know about astronomers, we're very imaginative with names. So we call these ones the long gamma ray bursts. These ones the short gamma ray bursts. Okay, so we have these 2 types of gamma ray bursts that suggest that perhaps there are 2 types of objects that are producing these gamma ray bursts. That somehow nature knows how to make things that look similar enough in 2 very different ways one which produces a gamma ray burst that just lasts shorter than other ones. Okay? So far I've told you how much energy these gamma ray bursts produce, and that they come from the far reaches of the universe, but I haven't actually told you what kind of objects produce gamma ray bursts. So that's what I want to touch on next. So from this list of 135 models, we've eliminated interstellar warfare. Okay? We've eliminated all models that predicted that gamma ray bursts come from the Milky Way. And we are essentially left with two classes of explanations, given the enormous amount of energy that's required. One is that gamma ray bursts are produced by the death of the most massive stars in the universe. Okay? These stars weigh as much as 100 or 200 times the mass of the sun. They have a very short lifetime. The sun's lifetime is about 10 billion years. The more massive a star is, the shorter its life. So these stars only last for a few million years. Okay? They're kind of like the rock stars of the universe. They burn fast and they die young. And they produce these enormous explosions. So here's a computer simulation of what happens when one of these stars dies. And here's a NASA illustration of the same process. So what we think is happening is that the star eventually runs out of fuel, it burns all of its fuel, and it is so massive that it can no longer support itself against its own gravity, and it collapses and produces a black hole at the center. And then the black hole powers these jets of material that penetrate out of the collapsing star and produce a burst of gamma rays. Okay? So it's a computer simulation showing that this process actually works on a computer. Here's the illustration showing the same thing. You can see the star collapsing on itself. The black hole is somewhere here in the center. The star is still collapsing. And it produces these jets of gamma rays. And eventually the star is gone, and all that's left behind is a new black hole. So that is one explanation, very popular. And that happens in a few seconds, yes. Here's another possible, very popular explanation, and which is the merger of two of these neutron stars that I mentioned earlier. Now, these neutron stars, like I said, they're about 1 to 2 times the mass of the sun in mass. They're about the size of the city of Boston or New York or your favorite city. They're extremely dense, and some of them are born in pairs. So they start with a system that initially was 2 very massive stars. Each one exploded as a supernova and left behind a neutron star. And over time, these neutron stars can spiral in, get closer and closer to each other until they collide and shred each other apart. So this is exactly what's shown here. This is, again, a computer simulation showing how 2 neutron stars merge together to form a black hole that will then suck in all of this material around and produce the jet of gamma rays. And here's again the nice NASA illustration showing the 2 neutron stars spiraling faster and faster together until they merge and produce a burst of gamma rays. Okay. So these are 2 models that people are very enamored with in the community of gamma ray bursts. They give rise to black holes. They can produce an enormous amount of energy. And most importantly, we know that these types of objects actually exist. We see them in the Milky Way. So how could we tell apart which model is correct? Well, we can look at where these objects are coming from inside their galaxies. They happen in galaxies very far away, but we can use telescopes like the Hubble to zoom in and peer at where these objects come from. And these models make predictions that, for example, if gamma ray bursts come from these very massive stars, and these very massive stars only last for a few million years, we should see them exploding essentially where they were born. Right? They haven't even had time to leave the cradle before they explode. And so we should see them in places like these, in star nurseries where stars are born. Okay, so here's a picture of a spiral galaxy. This is what the Milky Way would look like if we looked at it from the top. And these spiral arms, you can see they're lined up with these very bright knots of emission. These are all star nurseries. Okay? All of these places are places where new stars are born. They're lined up with the spiral arms of these galaxies. So if gamma ray bursts come from these star nurseries, we should see them lining up with spiral arms as well. Okay, so here's a Hubble image of a galaxy that had one of these long gamma ray bursts occur in it. And you can see the spiral arms of these galaxies, right? Over here. And this is the location of the gamma ray burst. You can see it's right up on the spiral arm. Okay? Exactly where we expect these star nurseries to be located. Another place in the universe where a lot of young stars are born is in places where two galaxies merge together. These are the famous antennae galaxies. These are two galaxies that came in and are now in the process of merging into a single galaxy. And if we look at this region, this entire region over here where the collision is taking place is full of these knots of very bright emission that are the locations of the birth of new stars. So again, if gamma ray bursts were the result of these massive stars, we'd expect to see them in galaxies that look like this, like a train wreck, essentially, right? Okay, so here are some more Hubble images of galaxies that had long gamma ray bursts in them. You can see this one is clearly a train wreck, and here as well. Here's another one. You can see these two galaxies are coming in and merging together, and this is where the gamma ray burst occurred, at the place where these two galaxies are colliding. Okay, so what this is telling us is that these long gamma ray bursts do seem to come from the death of these very massive stars. Okay? They come from the places where the massive stars are. Now, what about the other model, the mergers of neutron stars? Well, these kind of objects we expect to find in very different environments. This process of two neutron stars being born and then slowly spiraling until they merge together to form a black hole takes billions of years, not a few million years. And so by that time, after a few billion years have passed, these galaxies are no longer forming young stars, and they would look like this, just like boring, dead, elliptical galaxies. Okay? They're not as pretty as the spiral galaxies. They're very simple. They're mainly composed of very old stars. And that's what we'd expect to find our neutron star, binaries coming in together, emerging, and forming the short gamma ray bursts, perhaps. And in fact, this is what we find. These are images of the galaxies that produce short gamma ray bursts. So here's a galaxy over here, just looking like a boring spherical galaxy. There's another one over here. This is the Afterglow. You see the Afterglow is as bright as the entire galaxy, right? Just for that brief period of time. Here's another one, very boring galaxy. Okay? And so it seems like these short gamma ray bursts are in fact coming from these very old galaxies that contain only old stars. They do not have these young, massive stars like the ones that produce the long GRBs, the long gamma ray bursts. They have just these binary neutron stars merging together. And so just by looking at the locations of where these objects come from, we seem to be converging on a picture where nature produces gamma ray bursts in two very different ways, from collapsing very massive stars to form a black hole, or from taking two neutron stars and merging, smashing them together to form a black hole. And somehow to us, they look almost the same, even though they come from very different types of sources. So that's a lot of fun, but you can say, okay, so what have gamma ray bursts done for me recently? Right? Aren't they useful for something else? They are. So one of the interesting questions in astronomy that's driving a lot of what we're doing these days, and a lot of expenditures by NASA, like the James Webb Space Telescope, is how did the first stars and galaxies in the universe form? Okay? We know what the universe looks like today. It's beautiful, we see the sky, but we don't really know how it all started. We know there was a Big Bang over here, and we know what things look like here, and maybe we know all the way up to about 1 billion years after the Big Bang. But from here on, it's essentially a big question mark. And we essentially call it the dark ages. Okay? We don't really know what's happening there. Now, we can make computer simulations of what's happening in these early stages of the universe. And we think that the universe starts being very smooth and very simple. And over time, these first stars and galaxies form and produce what the universe looks like today. But we really want to see this happening in reality, not on a computer. So why are gamma ray bursts interesting for this purpose? Well, I've told you that these are the most brilliant sources in the sky. They're the biggest explosions since the Big Bang itself. And so potentially, if we could find some of these gamma ray bursts all the way back in the dark ages, they could illuminate the dark ages for us. Okay? And they can do it essentially in two ways. Imagine that we had a gamma ray burst exploding over here. The light from these bursts will have to travel through the entire universe to get to us. And so imprinted on that light will be the entire history of the universe. Okay? It's as if we're sitting in a dark room and we momentarily flip on the lights and we get a chance to kind of see what's around us. Okay? That's what the gamma ray bursts can do for us because they're so bright. In addition, we know that some of these gamma ray bursts come from extremely massive stars. And so if we can find the ones that are very far away, perhaps they can pinpoint for us the first stars in the universe. Okay? Think about this. We could use gamma ray bursts to find the first star that was formed in the universe. Okay? It's very exciting. Now, until recently, the most distant gamma ray burst that we knew about occurred about 1 billion years after the Big Bang. So right at the end of these dark ages, where we kind of know what's going on. But the challenge has been, for the past several years, for people like myself and others studying gamma ray bursts, to really find the ones in the dark ages. And I can tell you that we've succeeded, at least in several cases. So here are images taken with telescopes on the ground of the afterglows of 2 gamma ray bursts. They are so far away, their light is redshifted by such an enormous amount, that we only see them in the infrared part of the spectrum. They're no longer visible to the part of the spectrum that our eyes are sensitive to. They're just in the infrared. So you can see they're completely dark in the part our eyes would be sensitive to and very bright in the infrared. This object, when we measured its distance, has a redshift that is so large that it occurred only 630 million years after the Big Bang. And this gamma ray burst over here occurred only 525 million years after the Big Bang. So in our diagram, they happened right here. And we recently, just a few months ago, found another one at about the same distance. And so we finally now see gamma ray bursts from the dark ages of the universe, where we can see no other objects at the present. And it's thanks to the fact that these explosions are so bright that a single star can essentially appear brighter than any other object in the sky. So we know they exist there, and we know that they're giving us this tantalizing view of what the very early beginnings of the universe look like. And if we want to study them in much better detail, we need the next generation of telescopes. So here's a picture of a telescope, the giant Magellan telescope, that will hopefully be completed this decade, which Harvard and the Smithsonian Observatory are part of. Each one of these mirrors is the size of about the biggest telescope in the world today, and it has 7 of them. This will be built in Chile. Yeah. And so here's the size of one of the modern, cutting-edge telescopes today, and this is the size of what this beast is going to be. The first of these mirrors has actually been completed, and just to give you a scale, this is what the mirror looks like. Okay? This is just one. These are normal-sized people. So these mirrors are enormous. They're about 8 meters in diameter, and there are going to be 7 of them. Okay, so such an enormous telescope will really allow us to capture the light from these extremely distant gamma ray bursts, dissect the spectrum, and actually understand what the early stages of the universe look like. Okay, so hopefully I gave you a view of the biggest explosion since the Big Bang. It's been a fantastic 40-year journey since the discovery. I wasn't there for all of it. But again, fascinating story of a completely accidental discovery, and we're on the verge of, I think, solving a lot of the key questions. And really the next step is to use these gamma ray bursts to study the very early beginnings of the universe. So thank you.